In this video, we'll talk about the method of undetermined coefficients as a way to find solutions to non-homogeneous second-order differential equations. So based on our theorem from before, we know if we want to solve a non-homogeneous differential equation, something like this problem here, we know our solution will be of the following form. It'll be yp of t, where yp is any one solution that we can find for the non-homogeneous problem, plus c1y1 plus c2y2, where this last part here fit into the yc term, which solves the homogeneous problem where I drop that g of t off the end. If we had a constant coefficient case where p of t and q of t are both constants, we would know how to find this y1 and y2 and could build this c1y1 plus c2y2 part of it. In that case, we just have to find yp. And based on our results, we can find it however we want. As long as we come up with an example of a yp that solves the problem, we're good to go, and we can then find every solution for any initial condition using the fact that we have this C1 and C2 here. So we can find this however we want. You could guess it, you could be given it, any of that would work to get you to this yp. Once you have that, you can build a general solution by adding in the C1y1 plus C2y2 components. So there's two main methods. There's undetermined coefficients and variation of parameters, which are two ways to try to get to this yp. And we'll talk about the first of those here. Undetermined coefficients is a little bit simpler, but it only works in certain cases, whereas variation of parameters is more complicated, but works no matter what. And that's sort of the trade-off between these two different methods. So for this, let's look at an example here. We have y double prime plus 3y prime minus 4y equals 3e to the 2t. Let's get the easy part out of the way first. Let's solve the homogeneous problem. So for that, I pretend the right side is 0, and I'm looking for the characteristic equation again. In that case, it's going to be r squared plus 3r minus 4 equals 0, which factors as r plus 4r minus 1. So the general solution to that problem is going to be c1 e to the minus 4t plus c2 e to the t. And that we're going to box and save for later. We have that. That's going to be tacked onto the end of our yp to then solve the entire problem. But now we have to find the yp. So to find yp, which remember is any particular solution that solves the non-homogeneous problem. Let's just think about this problem. We have on the right side a constant e to the 2t. Great. On the left, we have derivatives and multiplying by constants. So I want to come up with an idea for what a function might look like. So if I take derivatives and multiply by constants, I get something like e to the 2t. Well, the answer there is e to the 2t, because exponents repeat themselves when you differentiate them. So since derivatives of e to the 2t still involve e to the 2t, something times e to the 2t might be a good candidate for this yp. We don't know yet, but we know if we find something that works, we're good to go to solve our problem, because once we find any singular yp of t, so we can guess whatever we want to get it, we know we then can solve the problem. So let's try yp of t is some constant a times e to the 2t. And this a is a constant we don't know the value of it. We're going to try to figure it out to make it solve the problem. This a is our undetermined coefficient. As mathematicians are super creative, it is a coefficient of this e to the 2t that is as yet determined, so it is an undetermined coefficient, is what it is. We're going to take this and we're going to plug this into our differential equation and see what happens. So if this is our yp, then yp prime is just 2a times e to the 2t, and yp double prime is 4a e to the 2t. And then let's plug in. So we had y double prime plus 3y prime minus 4y as the left-hand side of our equation. We can plug in our stuff for yp here. This is going to be then 4a e to the 2t plus 3 times 2a e to the 2t, and then minus 4 times a e to the 2t. I can simplify this out a little bit to get, I have 4a e to the 2t plus 6a e to the 2t minus 4a e to the 2t, which comes down to just 6a e to the 2t. Now, if I want yp to solve the non-homogeneous problem, I want this to equal 3e to the 2t. Because if I scroll back up, that was the right-hand side of the equation at the very beginning. So then with that, I can say I can make this happen by just setting a to be 1/2. So choose a to be 1/2 so that my function now, yp of t, is 1/2 times e to the 2t. And if we plug this back in, we will see this does in fact satisfy the non-homogeneous problem, which means we can take that yp, tack on our homogeneous equation from before, and get the general solution for the non-homogeneous problem is going to be y of t is this yp, 1/2 e to the 2t, and then plus my solution to the homogeneous problem, a c1 e to the minus 4t, and a c2 times e to the t. So that's the general solution there. The idea is figure out what sort of form this yp should be in based on the right-hand side of the equation, guess it with these undetermined coefficients in front, and then just plug them in and see what you have to pick the coefficients to be in order to solve the non-homogeneous problem, and then tack on the homogeneous part. So the main point that made this work was the fact that exponential functions repeat themselves when you differentiate them, right? If you start with e to the ax and differentiate, you get a times e to the ax. You still have this factor here out front times a constant, which means plugging them into constant coefficient equations, they keep their form as you differentiate, which makes it possible to guess them as solutions here. What else could do this? Well, polynomials also do this. They lose a degree every time, but if you start with a polynomial and differentiate, you keep getting polynomials, right? If I have something like at plus e, and I differentiate, I just get a. That's still a polynomial of one less degree. So if I saw a polynomial on the right-hand side, I could guess a polynomial with undetermined coefficients and try to solve that out and see what I would get, as do things like sine and cosine. Right, these two swap back and forth, but they stay within being sine or cosine always, right? If I have sine of 2t, I can differentiate that once and get to 2 cosine of 2t. If I differentiate twice, I'm at minus 4 sine of 2t, so I'm back at the sine that I started from. And the important thing is here, the argument inside doesn't change. It's still the same sine function, so I could guess that and hope that that might also get me to a solution using undetermined coefficients. So these are the main cases where this method sort of works, but in these cases it works out really well to find solutions to non-homogeneous linear constant coefficient equations.